Tonight we're letting our thoughts spiral gently outward, not into worry or stress, but into space. A slow, gliding descent into the arms of galaxies, curling like smoke through the dark. You've seen them, perhaps, in telescope photos, on a documentary late at night, or as a wallpaper glowing softly behind icons on your screen. These great swirling islands of stars, each home to billions upon billions of suns, all wrapped into elegant, spiraling arms. But why? Why the spiral? Why do galaxies across so much of the visible universe seem to favour this shape? There are no alarms in the cosmos, no ticking clocks, just light, spreading, bending, travelling across ages, and gravity, the quiet hand that holds it all together. Let's start there, with gravity. Not the kind that tips your cup off the table or pulls your blanket closer when you shift in your sleep. This is the slow gravity of the universe itself, vast, patient, and relentless. It shapes clouds of gas into stars. It turns stars into clusters, clusters into galaxies, and in many cases, those galaxies into spirals. Imagine a cloud, immense, diffuse, colder than you can imagine. A great interstellar haze, hundreds of light years across, filled with hydrogen, helium, and little else. Now imagine that cloud beginning to collapse, ever so slowly, under its own gravity, like dough folding in on itself. As it shrinks, something fascinating begins to happen. It starts to spin. That spin, that angular momentum, is one of the oldest, quietest tricks of physics. You can think of it like a cosmic ice skater. As she pulls her arms in, she spins faster. The same thing happens to that collapsing cloud of gas. It's not rotating quickly at first, maybe just a whisper of motion, a vague turning. But as the cloud contracts, the spin increases, faster and faster, and over time, what was once a formless fog becomes a flattened, rotating disk. This is the beginning of a spiral galaxy, but a disk is not yet a spiral. For that, we need structure, and the structure comes from patterns, waves to be specific. Not sound waves or light waves, but density waves. Ripples in the galactic disk, moving through stars and gas, like invisible traffic jams, where material slows down, bunches up, and forms something beautiful. You might be wondering, how can stars bunch up? Aren't they scattered, drifting freely? They are. But the spiral arms aren't made of fixed stars, locked in place like beads on a string. They're more like patterns, glowing ripples where stars pass through, like dancers moving across a floor of shifting light. A common metaphor compares spiral arms to cars on a highway. Some spots slow down, causing a build-up. The cars, or in our case stars and gas, move through the jam, but the jam itself lingers. That's how spiral arms behave, not permanent features, but moving regions of higher density, where stars form more easily, where light shines a little brighter, where gas compresses and collapses into new stellar generations. It's not a rigid structure, it's choreography, an elegant swirl of gravity and momentum, pattern and particle. There are different types of spiral galaxies too, grand design spirals, with clearly defined sweeping arms, flocculent spirals, with patchy, fragmented ones, and barred spirals, where the arms appear to unfurl from a central bar of stars, as though painted outward from the galaxy's core. Our own Milky Way is a barred spiral, by the way, a quiet reminder that you're living inside one of these cosmic swirls, even now, drifting slowly with the solar system through a galactic arm, like a dust mote caught in a vast glowing tide. But it's hard to feel the motion. We can't see it happening. The speeds are enormous, hundreds of kilometers per second, yet the scales are so vast that it feels like stillness. And in that stillness, we forget that we are orbiting not just the sun, but the center of our galaxy, a journey that takes about 230 million years to complete. You've made it part of the way already. Every night you sleep, every day you move, you're tracing that immense spiral arc. And maybe, just maybe, understanding why galaxies spiral will make that motion feel a little more like a lullaby, soft, continuous, and beautiful. Let's stay here a while longer, floating in that thought. The stars aren't in a hurry, neither are we. Now that we're nestled comfortably in the galactic disk, let's take a closer look at the spirals themselves. Not as static arms, but as whispers of movement, as density waves. It's tempting to think of galaxies as frozen photographs, locked in their spiraled pose. But the reality is far stranger and far more elegant. The spiral shape isn't carved into the stars themselves. It's the result of waves, slow sweeping patterns of compression that move through the disk of a galaxy like the echo of a song. This is the density wave theory, and it's one of the most compelling explanations for why galaxies spiral at all. Picture a merry-go-round made of stars, each one following its orbit, guided by gravity, pulled gently toward the galactic center. But instead of a solid platform, imagine it as a swirl of gas, dust, and stars all moving at different speeds, depending on their distance from the center. Closer in, stars orbit quickly. Further out, they drift more slowly. That difference in speed, called differential rotation, is key. Now introduce a pattern into that rotation, a slight overdensity, a ripple in the disk. As stars and gas pass through this region, they slow down just a bit, piling up. The density increases, more gas collects, and as the pressure builds, stars begin to form. Bright young stars, short-lived, hot and luminous, light up the spiral arms, marking them out like glowing brushstrokes across the galactic canvas. But here's the trick. The pattern rotates more slowly than the stars themselves. The stars move in and out of the arms, just like cars flowing through a traffic jam. The arm is an illusion of movement, a pattern, not a structure. It's beautiful because it's temporary, persistent, yes, but not fixed. And in that dance, galaxies find their shape. Not all stars are born equal. The brightest ones, the blue giants, and massive suns that shine fiercely and die young, are the ones that illuminate the spiral arms. They don't live long enough to travel far from the wave that birthed them. That's why the arms are so vividly lit. It's not because most stars are there, it's because the brightest ones are. Imagine watching a slow parade through a foggy street. You don't see the entire procession, just the lanterns. Glowing, flickering, marking the path. That's what we're seeing when we look at spiral arms from afar. The lanterns of young stars, lit briefly before fading into the galaxy. And yet the arms remain, because new stars keep forming, new gas keeps flowing in. The wave continues to travel, not stopped by time, just shaped by it. Spirals persist for hundreds of millions of years, sometimes longer, but they are not immortal. Eventually galaxies grow old, the gas runs out, the stars spread out, and the spiral begins to fade. But we're not there yet. For now, in galaxies young and bright, the spirals still shine. They hold the memory of motion, the rhythm of gravity, the soft pressure of time. You can think of them as a kind of galactic fingerprint, no two quite the same. Some are tight and tidy, others loose and lopsided. Some glow with starburst brilliance, others hum quietly in infrared, cloaked in dust and mystery. And all of them, all those spiraling galaxies scattered across the sky, are still moving, still turning, still weaving their slow cosmic spirals across the fabric of the universe. Let's float with them a little longer. It's a lovely night to drift through stars. Not all spiral galaxies are created equal. If you look closely, and by look, I mean point a telescope millions of light years outward and wait patiently for the light to arrive, you'll notice that many spirals have a distinct feature stretching through their centers. A bar. Not a drinking establishment in space, unfortunately, though that's a charming image. This is a bar of stars, a luminous elongated structure, like a handle anchoring the spiral arms as they wind outward. Our own galaxy has one. The Milky Way is what astronomers call a barred spiral galaxy. That central bar might not be something we can see with our eyes, what with all the dust and stars between us and the galactic core, but we can detect it through indirect means. The movement of stars, the distribution of gas, the way the arms are anchored. So what is it? Why a bar? It turns out that as galaxies age and evolve, their inner regions often become unstable. The stars in the central bulge, that spherical concentration of old stars near the heart of the galaxy, begin to rearrange themselves. Over time, some of that mass settles into a rotating bar. It's a natural consequence of gravity and motion, a sort of internal feedback loop. As the stars move, they tug on one another. Those small tugs build up, and before long a linear pattern emerges. You might be wondering, what effect does this bar have? Quite a few, actually. Bars act like galactic engines. They can funnel gas inward from the spiral arms toward the centre, where it feeds star formation, or, in some cases, even fuels the supermassive black hole lurking at the core of the galaxy. The bar acts as a kind of highway, drawing in fresh material and concentrating it where it can do the most, illuminating. In that sense, barred spiral galaxies are like living organisms with internal circulatory systems. The bar keeps things moving, keeps things breathing. Without it, gas might remain spread out, diffuse, too calm to collapse, but the bar stirs the pot, and in doing so, it helps keep the galaxy vibrant. Of course, not all galaxies have bars. Some are neat spirals with no central feature. Others may have had bars once, but lost them through gravitational interactions, mergers, or the slow diffusion of time. In galactic terms, a bar is a phase, a long one, but a phase nonetheless. And if we step back, way back, and look at spiral galaxies across the universe, we start to notice something intriguing. Bars seem to be more common in older galaxies. In younger galaxies, bars are rarer. That suggests bars might emerge later in a galaxy's life, a sign of maturity, perhaps even the beginning of a slow transition away from the tightly wound spirals of youth. Imagine galaxies going through cosmic life stages, childhood as irregular blobs, adolescence as smooth spirals, adulthood with bars and structure, and eventually, old age, elliptical, quiet, no longer forming stars. But we're getting ahead of ourselves. Right now, we're in the bloom of galactic life, spirals still spinning, bars still shining, arms still lit by the glow of young stars. The Milky Way, with its central bar and curling arms, is still active, still forming stars at a modest but steady pace, still a place of birth and brightness, even after billions of years. And somewhere, wrapped in one of those arms, about 27,000 light-years from the centre, is us, the solar system, a small golden thread in the tapestry, orbiting gently, tucked between clusters of stars and clouds of gas like a passenger on a carousel too large to comprehend. Sometimes it's easy to forget. We look up and see only a few thousand stars with the naked eye, but they are just a local sample. The Milky Way alone holds hundreds of billions, and we're in motion with all of them, carried silently through a spiral galaxy shaped by gravity, waves, and time. So the next time you look up, remember, that darkness isn't empty. It's structure, pattern, and above all, motion. We're all still spinning. Time in a galaxy is not measured in seconds or hours or even lifetimes. It flows more like glacier melt, imperceptibly slow, yet unimaginably powerful. The arms of a spiral galaxy can take hundreds of millions of years to complete a single turn. The Milky Way rotates once every 230 million years or so. That's one galactic year. In that time, on Earth, entire species rise and fall, continents shift, oceans open and close. And yet in the galaxy's own clock, it's just one tick. Think about that. When the solar system was young, Earth still molten and breathless, our star was already orbiting the galaxy. When the first simple life stirred in the oceans, single-celled and unaware, it did so while drifting through the galactic spiral. Dinosaurs came and went in a single galactic season, and human history? Just a blink, less than a blink. Galaxies are timekeepers of a scale so vast it's difficult for the mind to hold. But even galaxies change. Over time, the shape of a spiral can shift. Arms loosen, bars grow longer. The bright bursts of star formation begin to dim. The gas that fuels new stars starts to run dry. And bit by bit, the galaxy grows quieter. This is not sudden, not tragic, just change. Some spiral galaxies evolve into lenticular galaxies, disc-shaped, but without the beautiful spiral arms. Others may merge with neighbours, their structure disrupted by the gravitational ballet of cosmic collisions. When galaxies collide, as the Milky Way is destined to do, with the nearby Andromeda galaxy, in about 4 billion years, the result is not a violent explosion, but a slow, sweeping transformation. Stars rarely collide directly. There's too much space between them. But the gravity changes everything. The spirals may stretch, twist, or be pulled apart. New stars may form in great bursts of light. Eventually, the merger settles, and what remains is often an elliptical galaxy, a puffed-up, rounded structure full of old stars, dimmer, quieter, but no less majestic. Even spiral beauty has its season, and yet even now, new spirals are forming. In quiet corners of the cosmos, clouds of gas still collapse, still spin, still give rise to the spiral pattern. The galaxy factory hasn't shut down entirely. It simply works at its own pace. We live in the middle of this slow cosmic sculpture, at a moment of clarity, with spirals above and stories ahead. And so, we drift with them. Unhurried, unbothered, spiraling softly through time. If you could drift above a spiral galaxy, slowly, silently, and look down upon its glowing arms, you'd notice something intriguing. Colour. The spiral arms shine with a kind of quiet vibrancy. There's a soft bluish hue that dances along the curves, like morning mist catching the light. In contrast, the core of the galaxy, that dense central bulge, glows warmer, yellowish, even a little red, like embers tucked into the middle of a cosmic hearth. These aren't just aesthetic details. In astronomy, colour is a clue, a quiet signature written in light. That bluish tint along the spiral arms, it's the telltale glow of young stars, massive, hot, short-lived suns, burning their fuel with intense brightness. They live fast, die young, and illuminate their neighbourhoods while they last. These stars are only a few million years old, infants by galactic standards. And because star formation is most active in the spiral arms, this is where those blue hues shine brightest. The yellow-red core, on the other hand, is home to much older stars, cooler, dimmer, and far longer lived. These suns are ancient, billions of years old, quietly orbiting the galactic centre, whispering stories from an earlier cosmic time. So when you look at a spiral galaxy, even in a photograph, you're seeing time. The arms are the present, fresh and full of change. The core is the past, aged and stable. A galaxy is not just a structure in space, it's a structure across ages. And the colours don't stop at stars. Spiral arms also trace trails of gas and dust, the raw material for new generations of stars. If you switch to an infrared view, you'll see reddish streams winding through the spiral like smoke. These are cool clouds of molecular gas, often invisible in visible light, but glowing warmly when seen in other wavelengths. Astronomers use all of this, colour, temperature, emission lines, to piece together what's happening in a galaxy. It's a kind of forensic astronomy. Light becomes language. Every wavelength tells a different part of the story. In some galaxies, the spiral pattern is sharp and defined. In others, it's messy, patchy, with arms that break, reconnect, and curl in unexpected directions. These flocculent spirals, as they're called, are still governed by the same rules: differential rotation, density waves, and the quiet pull of gravity. But like people, galaxies come in all sorts of personalities. And sometimes something more dramatic steps in. Tidal forces from nearby galaxies can stretch and twist a spiral, distorting its symmetry. The elegant swirl becomes chaotic, broken, like a painting caught in a breeze. You might see arms flung outward like ribbons, or plumes of gas trailing off into intergalactic space. These tidal tails, as they're called, are the fingerprints of gravitational encounters. Even light can't always clean up the mess, but the beauty is still there, in the motion, in the complexity, in the change. No spiral is perfect, and that might be the most perfect thing of all. So as we drift through this gallery of galactic shapes and shades, let the colours speak. Let the arms, the core, the gas and dust, each whisper their piece of the puzzle. Not just where the stars are, but where they're going, where they came from, and how, in the end, it all spirals together into one breathtaking, slowly turning story. The universe is not still. It paints with light, it draws with gravity, and it always, always moves. It's easy to forget when we speak of galaxies as distant glittering things, that we live inside one. The Milky Way is not just a name, it's home. A barred spiral galaxy, roughly 100,000 light-years across, spinning quietly in a corner of the universe. From Earth, we can't see its full spiral form. We're inside the disk, after all, like trying to guess the shape of a forest from under a single tree. But we've built maps, models, simulations stitched from countless observations, and they all tell us the same story. We are passengers on a spiral journey. The Milky Way has 4 major arms and several smaller fragmented ones. These arms wind out from the central bar, sweeping through the disk like curved bridges of light. Our Sun, along with the Earth and everything you've ever known, resides in a minor feature called the Orion Spur, a small offshoot between the Sagittarius and Perseus arms. In galactic terms, it's a quiet neighbourhood. Not too crowded, not too empty. A nice balance of stars, dust, and the occasional supernova echoing through space. We orbit the centre of the galaxy at an astonishing speed, about 828,000 kilometres per hour, yet we feel nothing. The distances are too vast, the curve too wide. Our solar system completes one lap around the Milky Way every 230 million years or so, a galactic year, as we mentioned earlier. If you could rewind time and track Earth's position through this spiral path, you'd find that we've made about 20 revolutions since the planet first formed. Dinosaurs lived and died in a single galactic season. Humanity's entire recorded history, cities, stories, stars named and catalogued, occupies less than 0.002 of a galactic orbit. And yet here we are, riding the spiral right now, this very moment, a mote of rock trailing a golden sun, circling a black hole at the galaxy's core, all part of a greater, ongoing swirl. Ah yes, the black hole. At the heart of the Milky Way, like in many spiral galaxies, lies a supermassive black hole. Ours is called Sagittarius A, and it's about 4 million times the mass of the Sun. But don't worry, it's not sucking us in. We're far enough away and orbiting peacefully. It's less a monster, more a quiet anchor, an invisible pivot around which the entire galaxy dances. Black holes like Sagittarius A are not well understood. They form the cores of many galaxies, and their role in shaping those galaxies is an area of active research. Did the black hole form first, and the galaxy grew around it? Or did it grow later, as the galaxy evolved? The answer might be somewhere in between, or something we haven't imagined yet. What we do know is this: the Milky Way is alive with motion. Stars orbit, gas flows, The spiral arms twist slowly in their endless procession, and we, tiny conscious observers on a blue world, get to be part of that movement. We look up and see constellations, patterns etched into the sky by imagination and myth. But behind those familiar dots is a structure far grander. The band of light you see on a clear night, the Milky Way, in the literal sense, is the disk itself, seen edge on. A gentle arc of countless stars, too many to name, too faint to see alone, but together, bright enough to mark the path of home across the sky. It's humbling, isn't it, to think that the same spiral shapes we admire in distant galaxies also cradle us, that we're not separate from the cosmos, but woven into its spiral thread. The Milky Way turns, the arms sweep, the stars drift, and in the quiet space between them, we dream. Galaxies may seem eternal and isolated, slow-moving islands in an ocean of stars, but in truth the cosmos is full of encounters, interactions, close calls, and sometimes collisions. It might be hard to picture two galaxies colliding. After all, they're mostly empty space. A galaxy, like the Milky Way, contains hundreds of billions of stars. Yet the distances between them are so vast that even when galaxies pass through one another, individual stars rarely collide. It's not a smash of glass and flame. It's more like two swarms of fireflies drifting through each other in the dark. But gravity always notices. As galaxies approach, they begin to feel each other's pull. Their shapes stretch, twist, distort. Spiral arms are yanked outward. Tidal tails of stars and gas curl away like ink in water. Sometimes the collision is slow and drawn out, lasting hundreds of millions of years. A prolonged cosmic waltz. Sometimes it's more direct, a head-on plunge. In both cases, the result is transformation. Spiral galaxies, in particular, are sensitive to these gravitational dances. Their elegant arms can be disrupted, fragmented, turned into loops or shells. A single encounter can change a spiral into something entirely new. But here's the wonderful twist. Collisions often spark star formation. As gas clouds from two galaxies collide, they compress. New stars ignite. In some merging galaxies, we see brilliant bursts of light, newborn stars scattered through the wreckage, lighting up the chaos. One famous example is the antennae galaxies, two spirals in the midst of a merger, their arms stretched and intertwined. Streams of stars arc outward like antennae, giving the pair their name. And along those arcs, brilliant knots of new stars flicker to life. It's a strange paradox, isn't it? Destruction that brings creation, chaos that makes light. Our own galaxy is heading toward a similar fate. In about 4 billion years, the Milky Way will merge with the Andromeda Galaxy. They're on a slow collision course even now, creeping toward one another at about 110 kilometers per second. When they meet, it won't be a cataclysm, it will be a reshaping. Astronomers believe the resulting galaxy will be something new, perhaps an elliptical galaxy, rounder and less structured. The spiral arms will fade, the disk may puff outward. Some stars will be flung far into space, others will settle into new orbits. And perhaps, as always, new stars will form from the stirred-up gas, lighting the way forward for whatever future watchers may exist. By then, the sun will be old, the Earth perhaps unrecognizable, but the memory of spirals will live on, in shape, in motion, in starlight. Because galaxies are not static sculptures. They are stories in motion. And when those stories intersect, something new is always written. So if you ever see an image of a colliding galaxy, arms tangled, cores merging, light blooming through the shadows, remember that you're looking at a moment in a much larger tale. A slow, graceful unfolding that takes place over epochs. A spiral caught in transition. And always moving. Now let's shift focus, not to what we see, but to what we don't. For all their luminous beauty, spiral galaxies are hiding something invisible, silent, and massive. Something that doesn't shine or glow, something that anchors the spiral shape, even though we can't detect it directly. It's called dark matter, and despite the name, it's not ominous, just mysterious. Dark matter makes up the vast majority of mass in a galaxy. In fact, by some estimates, over 85% of the Milky Way's total mass is dark matter. The stars, gas, dust, everything you can see is just the tip of the iceberg. The spiral pattern, the rotation, even the galaxy's ability to hold itself together, all of it is influenced by this unseen scaffolding. We first suspected dark matter's existence by looking at how galaxies rotate. Based on Newton's laws, the stars farther from the centre of a galaxy should orbit more slowly, like the outer planets of our solar system. But that's not what we observe. Instead, the stars in the outer reaches of spiral galaxies orbit at nearly the same speed as those closer in, as if something invisible is pulling on them, providing the extra gravity needed to keep them from drifting away. That something is dark matter. We don't know what it's made of. It doesn't interact with light. It doesn't emit radiation. It doesn't reflect, absorb, or scatter photons, but it exerts gravity, and that gravity helps define the very shape of spiral galaxies. Without dark matter, the spiral arms would unravel. The stars at the edges would fly off into the void. The galaxy would lose its structure over time. But instead, they hold for billions of years, because they're cocooned in a dark halo of mass we cannot see. You can think of spiral galaxies like luminous leaves caught in an invisible breeze, their motion and shape guided by something larger, more hidden, yet deeply real. In computer simulations, when scientists model galaxies with dark matter included, the spiral forms emerge naturally. The rotation curves match our observations. The arms persist longer. The galaxies behave the way real galaxies do. When they remove dark matter from the equation, everything falls apart. That's the quiet power of the unseen. It's humbling, isn't it? To realize that most of the universe is not made of stars or gas or people or planets. It's made of something else, something silent, and yet crucial. Dark matter doesn't just hold galaxies together, it shapes them. It may have helped them form in the first place. In the early universe, tiny fluctuations in dark matter density created the gravitational wells where gas gathered, collapsed, and formed the first galaxies. Without it, the universe might still be a cold, diffuse fog. So even though we can't see dark matter, we can thank it for the stars, the spirals, the arms that curl like smoke across the sky, and for holding us in place all this time. There's something quietly magical about the way telescopes work, not because they magnify, but because they look backwards in time. When you observe a galaxy through a telescope, especially one far away, you're not seeing it as it is now. You're seeing it as it was when the light left it. For a galaxy 100 million light years away, you're seeing light that began its journey when dinosaurs still roamed the Earth. For galaxies billions of light years distant, you're peering into a time before Earth even existed. So when astronomers observe spiral galaxies at various distances, they're not just seeing different locations in space, they're watching a timeline unfold, a record of how galaxies and their spiral structures have evolved over cosmic history. And what we've found is that spirals are ancient, but they weren't always quite like the elegant, well-formed swirls we see nearby. In the early universe, a few billion years after the Big Bang, galaxies were more chaotic, patchy, clumpy. Many looked like twisted knots of stars and gas. Spirals existed, but they were rare and rough. Their arms were less defined, their disks more turbulent, like early sketches of the forms we know today. This makes sense. In those days, the universe was more active, more crowded. Galaxies were colliding more often, and gas was being pulled and compressed in wild, unpredictable ways. It was a cosmic adolescence, full of motion, messiness, and rapid change. But over time, the universe calmed. Galaxies had more time to grow undisturbed. disks settled, spiral patterns began to emerge more clearly, like ripples in a pond that's finally stopped being stirred. And by about 6 billion years ago, spiral galaxies became more common, more orderly. Their arms stretched out, their bars formed, their disks flattened and expanded. Today, spiral galaxies are one of the most prominent types in the universe, especially in regions where galaxy collisions are infrequent. In the cosmic suburbs, you might say, and each one carries a kind of memory, not just of light and motion, but of when it formed. By comparing nearby spiral galaxies to distant ancient ones, astronomers can trace the evolution of structure, the way spirals become more coherent, more defined as time marches on. It's like looking at a series of photos, some blurred, some sharp, and slowly watching a painting come into focus. And yet each spiral remains unique. Some are tight, like corkscrews. Others are loose, their arms flung wide like dancers mid-turn. Some have strong central bars, others just a hint of one. No two spirals are exactly alike, because each one formed under different conditions, with different neighbours, different gas content, different tides of time. When we look at them, we're seeing the universe's own long-form artistry, an experiment in shape, repeated, revised, perfected. And the spirals we see now are just the current draft. Given enough time, billions of years more, they too will change, disrupt, merge, evolve into something else. But for now, they shine, still turning, still speaking, still offering glimpses into a younger universe. So the next time you look at an image from a telescope, maybe a Hubble snapshot of a distant spiral galaxy, remember this. You're not just looking into space, you're looking into the past, and the spiral is waving from billions of years ago. We've spent time looking at spiral galaxies from the outside, admiring their structure, tracing their curves, floating gently above the disk like cosmic cartographers. But what happens inside those arms? What's it actually like to be there between the stars? Let's go in. Spiral arms aren't walls, they're not solid structures, they're regions, zones of higher density where gas, dust, and stars are more concentrated than in the space between them. From the outside, they look like glowing rivers of light. From the inside, they're vast, sparse, full of motion. Imagine floating through the Orion arm of the Milky Way, the very one we live in. It's not like flying through a neon tunnel. It's more like being in a countryside dotted with lampposts. You can see the next star only if it's very close. Most of the time, you're surrounded by darkness. The space between stars is enormous, even within a spiral arm. But there are features. Giant molecular clouds, for one. These are dense regions of gas and dust, hundreds of times the mass of the Sun, and many light years across. They are the cradles of star formation, hidden in the spiral arms like knots in the wood. Cold, dark, quiet, until gravity takes hold and stars begin to form. And when they do, it happens in clusters. Baby stars often arrive in groups, swaddled in leftover gas, shining with fierce brightness. Many are hot, blue, and short-lived. Others will live longer, cooler lives, but their births are dramatic. The intense light and winds from newborn stars carve bubbles in the surrounding gas, sometimes triggering more star formation in the shockwaves they create. These regions are what make spiral arms so radiant. The arms themselves aren't permanent fixtures of matter, but star formation is. It's always happening in the arms, or rather, in the density wave that defines the arm's location. Stars are born in the arms, but they don't stay there forever. Because remember, the arms aren't static structures. They're patterns. The stars move through them. Over time, young stars drift out of the arms and continue their orbit through the galactic disk. The spiral arms keep moving, and new stars form behind them. It's a cycle, a spiral treadmill, you might say. The result is that the arms are always lit up with new stars, like glowing footprints left by an invisible dancer. There's also dust, lots of it. If you could view a spiral galaxy in visible light, you'd see dark lanes threading through the arms. These are interstellar dust clouds, tiny particles made of carbon and silicates floating between the stars. They obscure starlight, scatter it, and redden it, much like smoke in a beam of sunlight. But in infrared light, these dusty lanes shine, warm, ghostly traces of structure, highlighting the skeleton of the spiral. They help astronomers map the hidden interiors of galaxies, the places where stars are born, and where light is still on its way. And among the stars and dust drift planets, moons, asteroids, comets, perhaps even life, most of it hidden, most of it quiet, yet all of it moving, spiraling, part of the pattern. So when we speak of spiral arms, we're not just talking about shapes, we're talking about nurseries, about places where stars ignite, where light is born, where the elements for life, carbon, oxygen, nitrogen, are forged in stellar cores and scattered in supernovae. The arms are the story's opening chapter, again and again. So here we are, readers of the sky, drifting through one of those very arms, looking outward, looking inward, and always, always turning. Close your eyes, just for a moment, and imagine a galaxy as a piece of music. Not a chaotic noise, but a slow, deliberate symphony, each star a note, each arm a phrase, repeated and harmonized over billions of years. The spiral shape isn't just about light or motion, it's about rhythm. Because galaxies don't spin like records. They don't turn as a single, solid whole. Instead, different parts rotate at different speeds, a phenomenon known as differential rotation. This creates the conditions for spiral arms to form, yes, but it also gives galaxies a kind of internal tempo, a beat. The stars near the center of a galaxy, close to the core, complete their orbits more quickly. Those farther out take much longer. So as time passes, the spiral arms would seem like they should wind tighter and tighter, like threads around a spool, but they don't. That's the winding problem, a long-standing puzzle in galactic astronomy. If spiral arms were made of fixed stars, they should wrap up tightly within just a few orbits. But they don't wind up, they persist. This is where the density wave theory comes in, explaining that the arms are not rigid structures, but moving patterns. A song, not a sculpture. And like music, these patterns can resonate. In fact, galaxies have resonance zones, where the orbital speeds of stars and gas sync up with the spiral pattern. In these zones, stars can be trapped, caught in a gravitational rhythm that helps maintain the structure of the arms. It's as though the galaxy is playing chords, certain orbits that are reinforced, repeated and echoed. You might be wondering, how do we know this? After all, we can't just drop a microphone into a galaxy and listen. But astronomers can observe the movement of stars and gas using Doppler shifts, spectral lines, and carefully built models to reconstruct the rotational dynamics of spiral galaxies. It's like reverse engineering a melody from its echo. And the results are stunning. You can see the arms rotate. You can trace how stars are born, live and die along the spiral flow. You can even detect oscillations in the disk, vertical motions, like ripples on a pond. Some of these may be caused by satellite galaxies passing by, nudging the disk like a finger brushing a spinning top. All of it feeds the music. There are theories that spiral arms themselves may rotate at a different rate than the stars within them, not unlike the way a wave travels through water, even though the water itself moves in circles. The arms are waves, the stars are the sea, and the sea is never still. Even dark matter contributes to this dance. Its gravity provides the quiet bass note, deep, steady, persistent, giving the galaxy structure and preventing it from unraveling. So when you see a spiral galaxy, whether through a telescope, a photograph, or your own imagination, you're looking at a song being played across billions of years. No beginning, no end, just motion, repetition, harmony. Not just a shape, but a score. And tonight you're part of that music, drifting along in a quiet measure, a single note in a galactic lullaby. We often picture galaxies as isolated islands in space, swirling alone, self-contained and serene. But the truth is, galaxies have neighbours. The Milky Way, for example, is not alone in its corner of the universe. It's part of a small collection known as the local group, a kind of cosmic cul-de-sac that includes around 80 galaxies, most of them small dwarf galaxies that quietly orbit the larger spirals like tiny moons. The most prominent members of this group are the Milky Way, Andromeda, and the Triangulum Galaxy, 3 spiral galaxies all within a few million light-years of each other, connected by the faint gravitational threads of mutual attraction. Andromeda, the closest large spiral to us, is perhaps the most famous. You can even see it with the naked eye, a faint smudge in the night sky if you know where to look. It's more massive than the Milky Way, though not by much, and its spiral arms are wide, loosely wound, and rich with stars and dust. Triangulum is smaller, but no less lovely, a delicate swirl of light, full of star-forming regions, and soft pinkish nebulae glowing with youth. What's fascinating is that even these galactic neighbours influence each other. Their gravity doesn't just hold them in orbit, it shapes their very forms. Subtle tugs can warp disks, bend arms, or even trigger new waves of star formation. In fact, it's possible that the Milky Way's current spiral structure was influenced by interactions with its companions. Andromeda and the Milky Way are on a slow, inevitable collision course. Yes, but long before that final meeting, their gravitational influence may already have stirred the pot, created resonances, tilted orbits, perhaps even nudged our spiral arms into their current configuration. It's humbling to think that even something as graceful as a spiral galaxy is shaped by relationships, by its environment, by the quiet pull of neighbours too far to see but close enough to touch the tide of stars. And then there are the dwarf galaxies. These small companions, like the large and small Magellanic Clouds, orbit the Milky Way and may one day be absorbed into it. Some already are. Their stars stretched into streams that thread through the halo of our galaxy like starlight veins. These mergers add mass, stir motion, and sometimes leave behind echoes in the form of ripples in the galactic disk. Even in stillness, galaxies remember. So spiral galaxies are not just shapes, they are participants. In dances, in collisions, in quiet, gravitational embraces that last for eons. They are not alone, and neither are we. The local group itself is drifting slowly toward an even larger collection, the Virgo supercluster, and beyond that, the Laniakea supercluster, a sprawling network of galaxies bound together by gravity and the flow of dark matter. So as you lie still tonight, know this. You are not just spinning in a spiral galaxy. You are falling through a larger cosmic web, carried by your galaxy, tethered to others, part of a moving, shifting, ever-unfolding story that spans not just space, but kinship. Galaxies are never truly alone. They spiral in context, in company, and always in motion. If you've ever stood by the sea and watched the tide roll in, you've seen the subtle but powerful work of gravity. The moon pulls the oceans into motion, gently, predictably, eternally. Now scale that up, from oceans to galaxies, from the moon to entire galaxies, passing each other like ships in the dark. Galactic tides are real. Not tides of water, but tides of stars. Gravitational forces strong enough to stretch an entire spiral galaxy, reshaping it over millions of years. These tidal forces occur when a galaxy passes close to another, not necessarily a direct collision, but a near miss. One galaxy's gravity pulls on the stars of the other, and vice versa. But because gravity weakens with distance, the near side of a galaxy is pulled more strongly than the far side. This difference, this stretching, is what we call a tidal force. And it leaves fingerprints. A once symmetrical spiral may become distorted, its arms tugged into long streamers, its disk may warp, its stars knocked into new orbits. In some cases, entire tidal tails are created, arcs of stars, and gas flung outward like ribbons from a spinning top. One of the most famous examples is the Whirlpool Galaxy, or M51. This galaxy is a nearly perfect face-on spiral, but with a twist. One of its arms is stretched dramatically outward, and nestled beside it is a smaller companion galaxy. The two are locked in a gravitational embrace, the smaller galaxy having passed nearby not once, but likely multiple times, stirring the larger into its now iconic shape. Without that companion, the whirlpool might have been just another quiet spiral, but the interaction triggered new star formation, lit up the arms with fresh light, and gave us one of the most picturesque galaxies in the sky. Sometimes, beauty is born from disturbance. Other galaxies show signs of even more dramatic pasts. Disks that are warped, arms that are offset, bridges of stars connecting them to companions like filaments of light. These features fade over time, but for millions of years, they remain as gentle reminders. Someone passed this way. Even our own Milky Way has tidal scars. It's currently interacting with several dwarf galaxies, and evidence suggests that our disk is slightly warped, not flat but curved like a smile. This may be the result of gravitational nudges from passing companions or the aftershocks of past mergers. You might not feel it, but you're living in a galaxy that's still reacting to ancient encounters. It's a soft kind of memory, not written in books but in the curve of arms, the motion of stars, the slight twist of the galactic plane. Galaxies remember, and sometimes spirals are how they choose to show it. Like everything in the universe, spiral galaxies have a beginning, a middle, and eventually an end. But don't worry, endings in the cosmos are rarely abrupt. They come slowly over billions of years, more like a sigh than a bang. The story begins with gas, hydrogen and helium, drifting through the early universe after the Big Bang. These elements clump together under the influence of dark matter, forming the seeds of galaxies. As the gas collapses, it begins to rotate, and as we've seen, that rotation leads to a flattened disk, and eventually to spirals. Over time, stars are born within that disk. Some spiral galaxies experience starbursts, short periods of rapid star formation, often triggered by interactions with other galaxies. Others grow more slowly, steadily building their arms, star by star, but all of them depend on one thing: fuel. Star formation requires gas, cool, dense molecular gas, and as stars form, they begin to use up this gas. Some of it gets recycled, blown out by supernovae and stellar winds, only to cool and collapse again. But over the eons, more and more of it becomes locked away in stars, or heated beyond the point where it can condense. And so, galaxies age. The spiral arms become less active. Fewer new stars form. The blue light of young suns fades, replaced by the amber glow of older stars. The galaxy becomes quieter, redder, dimmer. Eventually, the spiral arms may fade altogether. The disk may puff up, losing its thin shape. The galaxy may take on a more rounded, featureless form, what we call a lenticular galaxy, still disk-like, but without the vibrant structure of its youth. Some spirals avoid this fate for a very long time. Interactions with gas-rich galaxies can rejuvenate them, giving them new material to form stars and renew their structure. But eventually, even the most vibrant spiral slows down. This process is known as galactic quenching. It's not a death, more like a retirement, a winding down. The stars that remain will still orbit, still shine. But the fireworks are over. The spiral, once a glowing river of motion and birth, becomes a quieter current. The galaxy still moves, still lives, but no longer sings with the same youthful brightness. And yet there's something beautiful about this too. The serenity of age, the grace of persistence, a spiral galaxy. In its twilight is no less grand, only softer, a candle after the flame, still warm with memory. And the spiral shape, though it may fade, leaves its echo in the stars it made, in their orbits, in their distribution, in the very structure of the galaxy. The dance leaves footprints long after the music stops. So as we float here in one of the Milky Way's arms, remember, you are living in the middle of a galactic story, not at the beginning, not yet at the end, but somewhere in the beautiful turning middle. The spiral is still turning, and we are turning with it. As we drift farther into our quiet exploration, it's worth noting that not all spirals are created equal. Astronomers, being natural classifiers, have spent decades categorizing the different flavors of spiral galaxies. And while the stars themselves don't particularly care what we call them, these categories help us understand the subtle differences, the nuance, in how galaxies grow, change, and express their spiral identity. Let's begin with the most iconic, the Grand Design spiral. These are the poster children of the spiral family. Their arms are well-defined, symmetric, and often extend gracefully from the center like the coils of a nautilus shell. Classic examples include M51, the Whirlpool Galaxy, and M81 in Ursa Major. These galaxies look almost staged, as though posing for a cosmic portrait. Grand design spirals are often influenced by nearby galaxies, a companion tugging gently on one side, stimulating those perfect arms into formation. It's a gravitational duet, creating beauty from the dance. Next, we have the flocculent spirals. The word flocculent means fluffy or woolly, and these galaxies live up to the name. Instead of long, smooth arms, they display patchy, fragmented patterns of stars and gas. It's as if someone took the brushstrokes of a grand design spiral and dabbed them randomly across the canvas. Don't let their messiness fool you. These galaxies are just as structured beneath the surface. The spiral pattern may be more subtle, more influenced by internal processes than by external forces. But they still follow the rules of gravity, density waves, and differential rotation. They just express them differently. Then there are multi-arm spirals, galaxies with more than two primary arms. Some have 3, 4, or even more, often winding out in unequal lengths or directions. They appear almost chaotic, like pinwheels caught in a gust of wind. Yet they too are stable over time, a testament to the adaptability of spiral structures. And of course, we can't forget the barred spirals. As we explored earlier, these galaxies have a straight bar of stars running through the center, with spiral arms unfurling from either end. The Milky Way is one of them. Bars are thought to emerge as galaxies age, redistributing mass and gas toward the core. They're like highways, directing traffic inward, fueling new star formation, or feeding the central black hole. In the Hubble classification system, a widely used tool for sorting galaxies, spirals are labelled with the letter S, while barred spirals are marked SB. From there, the subtypes range from A to C based on how tightly the arms are wound and how large the central bulge is. So you might see a galaxy labelled SBC, a barred spiral with loosely wound arms and a small core, or an SA, a tightly wound spiral with a large prominent bulge. It's not just alphabet soup. These labels offer clues about the galaxy's age, its dynamics, and its environment. And sometimes even more exotic variations appear. Spirals with rings, where the arms wrap around the galaxy like a hoop. Spirals with counter-rotating cores, where the center spins one way and the arms the other. Galaxies in transition. Galaxies mid-merger, galaxies reshaped by invisible hands. The spiral family is vast, and every member tells a different version of the same story. from elegant to fragmented, from structured to strange. And yet they all speak the same language: motion, matter, and time. So as we float through this quiet zoo of spirals, take a moment to appreciate the variety. Each galaxy, each swirl, is the product of billions of years, shaped by physics and chance, and viewed by us across a gulf of space and light. Each spiral is a signature, and no two are the same. We've talked a lot about what we see in spiral galaxies: their arms, their stars, their hidden cores. But how do we know how these structures form? How can we test our theories when the timelines stretch for billions of years and the laboratories are, quite literally, the size of the universe? We build galaxies in computers. Welcome to the quiet art of galactic simulation. Astronomers and physicists use supercomputers to create digital universes, artificial galaxies governed by the same laws of physics that rule the real ones. These simulations take into account gravity, hydrodynamics, gas cooling, star formation, supernova feedback, and dark matter, all rendered in code step by step over cosmic time. It begins with a volume of space, empty except for a cloud of gas and a halo of dark matter. The simulation gives it a slight rotation, a bit of unevenness, and then it lets gravity do the rest. Over time, the gas collapses, a disk forms, stars ignite, spiral arms begin to appear, first as whispers, then as full, glowing structures. Bars may form, mergers may occur, and all of it unfolds over thousands of simulated frames, a galactic life, compressed into hours of computational effort. One of the most famous simulations is Illustris, a massive project that recreated the evolution of the universe from just after the Big Bang to the present day. It contains thousands of galaxies, each with its own path, its own structure, its own spiral fate. These simulations don't just look pretty, they let scientists test hypotheses. What happens if you change the amount of dark matter? What if two galaxies pass each other at a different angle? What if you tweak the laws of star formation or the feedback from supernovae? How sensitive are spirals to their environment? By adjusting the dials, we can see how galaxies respond, which shapes are stable, which ones emerge naturally, which ones require outside interference, like a passing companion or a recent merger. And here's the quiet revelation: when all the variables are set just right, spiral galaxies emerge naturally. The physics of rotation, gravity, and pressure, the fundamental rules of matter, seem to favour the spiral shape. It's not just a curiosity, it's a consequence. That tells us something important. Spiral galaxies aren't rare accidents. They're expressions of the universe's default settings, the outcome of motion and time applied to a disk of matter. Of course, no simulation is perfect. We're still refining the models, adding more layers, including magnetic fields, black hole activity, and radiation pressure. But with each generation, the spirals get better, more accurate, more alive, and occasionally one of those simulated galaxies looks eerily like the Milky Way. Same mass, same bar, same curling arms, and you realize you're seeing not just a picture, but a possibility. The same forces that shaped our home are at work everywhere. In real space, in virtual space, in any space where gravity spins its spiral stories. Because much of what happens in a spiral galaxy is hidden, invisible, unless you know where and how to look. Let's start with infrared light. Unlike the visible spectrum that our eyes rely on, infrared light can pierce through dust. In many galaxies, especially the richly structured spirals, dust lanes snake through the arms like charcoal brushstrokes. They block and scatter visible light, obscuring much of what lies within. But infrared reveals what the dust hides: stars still forming, wrapped in blankets of cool gas. In this wavelength, a spiral galaxy takes on a different personality. It glows from the inside, like embers behind a screen. The arms remain, but they shimmer with a softer glow, tracing the heat of life rather than the brilliance of death. Then there's radio astronomy, a window into the coldest components of galaxies. Through radio waves, we can detect neutral hydrogen gas, the raw material for future stars. It extends well beyond the visible disk of a galaxy, forming vast ghostly spirals that stretch into the galactic outskirts. These arms aren't lit by starlight, but they trace the gravitational pull just as clearly. In fact, in radio wavelengths, many spiral galaxies appear far larger than they seem in optical light. Their true reach, their gaseous halos, can be several times wider than their starlit centers. Imagine that, spirals within spirals, some glowing with light, others waiting in the dark. And then there's ultraviolet. Young hot stars burn fiercely in ultraviolet wavelengths, and by observing a galaxy in UV, astronomers can pinpoint regions of intense star formation. These hotspots pepper the spiral arms like glowing embers, revealing where the next generation of stars is being born. Each wavelength tells a different part of the spiral story. In X-rays, we see the aftermath of supernovae, the violent deaths of massive stars. In gamma rays, we see the whispers of high-energy interactions. In submillimeter light, we trace cold dust and molecular clouds. A spiral galaxy, seen through all these layers, becomes more than just a shape. It becomes a system, a process, a layered structure of energy and motion, where every frequency reveals a hidden rhythm. And sometimes when we look at a spiral galaxy across the full spectrum, combining optical, infrared and radio, we find structures we never imagined. Extended arms far beyond the disk, hidden companions, rings of gas with no stars, even the echoes of past collisions, preserved in cold gas long after the light has faded. It reminds us that the universe doesn't just glow, it hums. And the spiral is not just a glowing pattern, but a resonance across the full orchestra of light. So the next time you see a photograph of a galaxy, bright arms curling against a dark background, remember, that image is just a single voice in a much larger harmony. One note in a cosmic song made of wavelengths far beyond what our eyes can perceive. Because galaxies, like dreams, are often brightest in the places we can't quite see. At the center of nearly every large galaxy, spiral or otherwise, lies a secret, a stillness so massive, so dense, that not even light can escape it, a supermassive black hole. These giants, millions to billions of times the mass of our Sun, are the quiet anchors of galaxies. They don't dominate the entire structure. Most of a galaxy's mass is spread throughout its disk, stars and halo, but the black hole is always there, at the center, turning silently, growing slowly. In the Milky Way, this object is called Sagittarius A. It's relatively small as black holes go, about 4 million solar masses, and yet it shapes the orbits of stars in the central bulge, tugs on clouds of gas, and serves as the gravitational core around which everything revolves. We can't see it directly, of course, but we've watched stars orbiting it at dizzying speeds. We've detected flares of X-rays and radio waves as gas brushes too close and heats up on its way in. In 2022, astronomers even produced a shadowy image of it using a worldwide network of telescopes, a hazy ring surrounding a dark center. Proof that even in darkness, presence can be revealed. But what do black holes have to do with spiral arms? More than you might expect, the black hole influences its neighborhood, especially in the early stages of galaxy evolution. As matter spirals inward toward the core, it heats up and releases enormous energy. This process, called accretion, can power active galactic nuclei, brilliant beacons that outshine the rest of the galaxy. These active cores can drive galactic winds, blowing gas outward and influencing star formation in the disk. Too much activity, and a black hole can quench its host galaxy, stripping away the gas that fuels spiral arms and ending the formation of new stars. But in quieter galaxies, like our own, the black hole simply sits, waiting, feeding slowly, barely influencing the arms, but still anchoring the whole. There's something poetic about it, a spiral galaxy, all motion and light, circling a centre that is silent, dark, and invisible. A dance around a void, and yet without that centre, the dance loses meaning. It's a reminder that not everything important shines, that some of the most powerful forces in the universe work quietly, in the background, holding structure in place, while the visible world moves around them. And perhaps that's the nature of the spiral too, a visible trace of invisible rules, a shape drawn by forces we feel but cannot see. Gravity, rotation, time, dark matter, and at the centre of it all, a singularity, patient, waiting, still. The arms may turn for billions of years, but always they turn around something deeper, and in that stillness, the spiral finds its shape. Let's pause just for a moment and think about something close to home. Not galaxies, not spiral arms, but you, the calcium in your bones, the iron in your blood, the oxygen you breathe. These weren't forged on Earth. They were created long ago, in stars. And many of those stars were born in spiral arms. In a way, you are spiral formed. Spiral galaxies, as we've seen, are factories of star birth. And inside these glowing arms, nestled in cold clouds of gas and dust, the universe performs its oldest magic, fusion. Hydrogen becomes helium, helium becomes carbon, then oxygen, neon, silicon, and in the final furious moments of a star's life, iron. Heavier elements, gold, uranium, platinum, form in even more violent events, supernovae or collisions between neutron stars. But the spiral arm is where it begins, a nursery, a crucible. It's easy to imagine stars forming as solitary miracles, single sparks flaring up in a dark void, but in truth, stars are born in groups, sometimes dozens, sometimes thousands, all from the same giant molecular cloud collapsing under its own weight. The most massive stars burn bright and hot, blue, dazzling, and short-lived. They last only a few million years before dying in spectacular supernovae, enriching their surroundings with heavy elements. These explosions send shockwaves through nearby gas, triggering the next generation of stars, a kind of cosmic recycling, and it all happens right there, within the arms of the spiral, over and over again. Meanwhile, the smaller stars, like our Sun, take a slower path. They burn gently for billions of years, living quiet, stable lives, and eventually they swell into red giants, shed their outer layers, and leave behind glowing cores called white dwarfs. Even these stars contribute, returning enriched gas to the interstellar medium through gentle winds and planetary nebulae. The spiral arm doesn't just shape the motion of stars, it shapes their composition. In the Milky Way, we can actually measure how the chemical richness of stars changes depending on where they are. The centre of the galaxy, where stars have formed and died in quick succession for billions of years, is more metal-rich, the outer arms less so. This radial metallicity gradient tells a story, one of ongoing creation, expansion, and evolution. A spiral arm is a timeline, a forge, and a laboratory. And you, your atoms, your cells, your thoughts, are its product. You are, in a very literal way, made of stardust, born in a spiral galaxy. Not metaphor, not poetry, just truth. The next time you look at your hands or feel your heartbeat, remember, parts of you once lived in the core of a star born in a spiral arm, a star that lived and died and scattered its ashes into the galaxy. And some of those ashes became you. We've admired the spirals, their beauty, their motion, their silent elegance. But even these grand structures do not last forever. Spiral galaxies are not eternal. They are a phase, a luminous chapter in the longer story of galactic evolution. So what comes next? Eventually, most spiral galaxies, given enough time and the right encounters, will become something else: elliptical galaxies. These are the ancient ones, massive, rounded and quiet. No spiral arms, no disks, no fresh star formation lighting the gas. Just a smooth reddish glow from old long-lived stars. They are galaxies in retirement. But how does the transformation happen? In most cases, it's through galactic mergers. When two spiral galaxies collide, their ordered disks are disrupted. The stars, once orbiting in neat spiral paths, are thrown into random directions. The gas is compressed, triggering a final burst of star formation. Then the gas is either consumed or ejected, and the spiral structure is destroyed. What's left behind is a puffed-up, spheroidal collection of stars, no longer turning in spirals, but moving in all directions. The galaxy has become elliptical. Sometimes, multiple mergers over time build up even larger ellipticals, vast, featureless giants sitting at the centers of galaxy clusters, formed from the remains of dozens of spirals. These galaxies are no less majestic, but they are quieter. Their stars are old, their light red and steady. Their gas is hot and diffuse, not the cold, dense clouds needed for new stars. The spiral arms, once active and bright, are long gone. This is galactic senescence. It's not sad, just different. A spiral galaxy is full of change, birth, motion, transformation. An elliptical galaxy is the memory of all that, a fossil, a monument. And yet the story isn't always so linear. Some spirals manage to hold onto their shape for billions of years. Others may be reborn. If new gas is acquired from outside, they can begin to spin again, forming fresh stars and reforming their arms. These are called rejuvenated galaxies, old systems with new life. Galaxies are dynamic. They resist simple definitions. Still, the spiral phase remains the most active chapter in a galaxy's life. The time of growth, of invention, of brightness, of motion. So while we may look ahead and know that spirals fade, we can also celebrate the now, the present, this moment. Because right now, you are living in a spiral galaxy that is still alive, still forming stars, still drifting through its arms, still turning around a black hole in the center of a disk. And that makes this moment, right here, right now, an extraordinary one in the life of a galaxy. A moment of spiral light, of spiral breath, and of spiral dreaming. Spiral galaxies often look like they're alone, singular wonders in the dark. But solitude in the universe is rare. Most large galaxies, spirals included, are orbited by satellite galaxies, smaller companions, often too faint to notice without sensitive telescopes. And while they may seem minor, these satellites can have profound effects on their host spirals. Let's take the Milky Way, for example. We know of at least 50 satellite galaxies surrounding it, some bound tightly, others trailing in elongated orbits. Two of the most prominent are the Large and Small Magellanic Clouds, visible from the southern hemisphere as faint smudges in the night sky. These aren't just passive passengers. They interact with our galaxy. Their gravitational pull stirs our spiral arms, possibly warps our galactic disk, and may even funnel gas into the Milky Way's inner regions. They're more than neighbours, they're sculptors. In fact, many spiral galaxies are believed to owe their very structure, or at least some of its more dramatic features, to the long-term influence of these small companions. You can imagine the spiral as a surface of water, calm and wide. A passing satellite is like a pebble tossed in. It creates ripples. Over time, those ripples become arms, curves, patterns. They trigger density waves, which compress gas and ignite star formation along the spiral structure. Sometimes satellite galaxies get too close. They fall in, they merge. In these moments, we witness something called minor mergers. smaller galaxies being swallowed by larger ones. And unlike the catastrophic collisions between giants, minor mergers don't destroy spiral structure. They often enhance it. They bring in new gas, new stars. They stir the disk just enough to keep things lively. There's evidence that some of the most beautiful spiral arms in the universe were shaped by such interactions. Subtle tugs, gentle mergers, repeated over time, sculpting the spiral like wind shapes a sand dune. It's not just gravity that matters, it's timing. A companion that passes by once may not do much, but one that orbits again and again, gradually losing energy, coming closer each time, can build structure with each pass. A dance of persistence. And so even the smallest galaxies play a role in the spiral story. They bring change, they bring movement, they bring texture to the grand design, and sometimes even survival. There are cases where satellite galaxies have helped preserve spiral structure by adding fresh gas and reviving star formation in disks that were fading into stillness. The spiral is relit, the dance continues. Even galaxies need company. So if our own Milky Way owes its spiral beauty in part to a small, wandering companion, that's not just poetic, that's history. Written in stars. To live inside a spiral galaxy is to be in constant motion. Not just you, or the Earth, or even the Sun, but everything. Every star, every cloud of gas, every dark matter particle is on the move, orbiting, circling, turning through the spiral arms like cars on a galactic highway. And while we often imagine galaxies as rotating disks, flat and two-dimensional, their motion is far more complex, more layered, more alive. Let's begin with the basics. The Sun orbits the centre of the Milky Way at a speed of about 828,000 kilometers per hour, fast enough to cross the continental United States in just 20 seconds. And yet the full orbit takes around 230 million years. That's one galactic year. So, in human terms, you've completed about 1/25th of an orbit in your lifetime. We are passengers on a colossal ride, one that started long before us and will continue long after we're gone. But it's not just simple rotation. Stars in spiral galaxies also exhibit small deviations, vertical bobs above and below the galactic plane, radial waves in and out, tiny oscillations that create a rich dynamical texture. The disk breathes, it ripples, it flexes. And then there are the spiral arms themselves. As we've seen, these aren't rigid structures. They're density waves, moving patterns of compression, like traffic jams on a circular highway. Cars or stars enter and exit the jam, but the location of the congestion, the arm, remains relatively fixed. So a star, like the Sun, passes through the spiral arms over time. Each passage takes tens of millions of years, and each time the star encounters a denser, more active region of the galaxy, rich in gas, dust, and young, massive stars. It's thought that these arm crossings may affect everything from comet activity to the climate of planets, as gravitational nudges disturb distant clouds and send objects inward. In this way, even Earth's history may be tied to our position in the spiral. And then there's the pattern speed, the rate at which the spiral pattern itself rotates around the galaxy. This speed is different from the orbital speeds of the stars. It's slower, more deliberate, and where the two match, where a star's orbit syncs with the spiral pattern, you get a region called the co-rotation radius. At this radius, stars can linger in the spiral arm for longer periods, leading to stronger interactions, prolonged exposure to star-forming regions, and possibly even subtle effects on stellar evolution. The Milky Way's co-rotation radius may lie just outside the Sun's orbit, suggesting that our solar system dips in and out of the spiral pattern, surfing gently along its edges. And beyond motion within the disk, the entire galaxy is moving. Our Milky Way is hurtling through space, being pulled toward the Virgo cluster. It orbits the local group's center of mass, It vibrates, shifts, leans. The dark matter halo surrounding it also moves, responding to the tides of cosmic structure. It's motion within motion, galactic ballet. The spiral arms are just the visible part, the dancers we can see. But behind them is an orchestra of motion, playing on invisible instruments. The more we learn, the more we see the galaxy not as a static object, but as a living system, moving, growing, changing, and turning, always turning. And we ride it like stardust on a wheel. Everything we've seen so far, the graceful arms, the starbirth, the motion, all of it rests on something we cannot see. Something silent, something invisible, something called dark matter. It doesn't emit light, doesn't absorb it, doesn't interact with normal matter in the usual ways, and yet its gravity, its pull, is absolutely essential to the structure of spiral galaxies. Without it, spirals might not even exist. Let's break it down. In the 1970s, astronomer Vera Rubin made a remarkable discovery. She measured the rotation curves of spiral galaxies, the speeds at which stars orbit at different distances from the center. Based on Newtonian physics, the expectation was simple. The farther from the center, the slower the stars should orbit, like planets in the solar system. But they didn't slow down. In fact, in many galaxies, stars in the outskirts were moving just as fast, sometimes faster, than those closer to the center. It made no sense unless something unseen was providing additional gravitational pull. That something was dubbed dark matter, and today we believe that spiral galaxies are embedded in vast dark matter halos, spherical clouds of invisible mass that extend far beyond the visible disk. The stars, the gas, the arms, the black hole in the center, all of that, just the tip of the galactic iceberg. Most of a spiral galaxy's mass, about 85%, is dark matter. It's what allows the disk to spin so fast without flying apart. It's what holds the spiral arms in place. It's what gives the galaxy structure, longevity, and stability. Without dark matter, spiral arms would wind up quickly and vanish. Galaxies would be smaller, more chaotic, and less cohesive. The beautiful patterns we see would unravel. But with dark matter, the gravitational grip is strong. The arms can form and persist. The stars can orbit smoothly. The spiral can live. And yet, we still don't know what dark matter is. We know what it's not. It's not made of atoms. It's not just faint stars or cold gas. It doesn't interact with electromagnetic forces. But it's there. It shapes galaxies. It bends light. It clumps, flows, and sculpts the cosmic web. In simulations, when we include dark matter, spiral galaxies emerge naturally. When we leave it out, they fall apart. It's like drawing a painting with invisible ink. You can't see it directly, but without it, the picture makes no sense. Some theories suggest dark matter particles may one day be detected, perhaps through particle colliders or subtle signals in underground detectors. Others propose that we may need to revise our understanding of gravity itself. But for now, we accept the mystery, because the evidence is overwhelming, and the spirals speak for it. Every curve, every motion, every glowing arm is a testament to something unseen. So the next time you look at a galaxy, or imagine our Milky Way spinning through space, picture the halo around it. Not glowing, not visible, but vast, protective, cradling the spiral like a ghostly hand, guiding the stars, shaping the light. We've come far, from the dusty arms of the Milky Way to the bright spirals of distant galaxies. We've traced the origins, motions, and meanings of the spiral form. We've peered into simulations. We've listened to the music of galactic motion. We've floated beside stars and sunk into the quiet pull of dark matter. And yet, the spiral still holds secrets. Despite all we know, and all we've guessed, many aspects of spiral structure remain mysterious. Why do some galaxies form spiral arms, while others don't? Even among galaxies with similar mass and gas content, some become spirals, others irregular blobs or ellipticals. Why? Is it timing, environment, dark matter distribution, or simply chance? Why do some spiral arms remain stable for billions of years, while others break apart quickly? Even within the same galaxy, arms can behave differently. Some fragment, some merge, some remain crisp and bright, others dissolve. The density wave theory explains a lot, but not everything. New models suggest chaotic spirals can arise without waves, just from internal turbulence and feedback. What exactly triggers a bar to form in a spiral galaxy? We know that about 2/3 of spirals have central bars. But why do they appear? What makes one galaxy grow a bar while another doesn't? And why do bars seem to fade in some galaxies over time? Are bars a phase or a final form? Do spiral patterns influence the development of planetary systems? We suspect that passing through a spiral arm can disturb comets, nudge orbits, and possibly trigger changes in planetary environments. But these effects are hard to study across such vast timescales. Is Earth's history linked to spiral crossings? Could intelligent life be more likely in certain spiral regions? How did the first spiral galaxies emerge in the early universe? We've seen spirals as far back as 11 billion years ago, mere moments after the first galaxies formed. How did such complex structure arise so quickly? Were these early spirals different in kind? Were they shaped by different forces? And then there's the biggest mystery of all. Why the spiral? Why does the universe favour this shape? In galaxies, hurricanes, nautilus shells, and even the twist of DNA? Is the spiral just a mathematical consequence of rotation and gravity? Or is it something deeper, a universal pattern etched into the fabric of physics itself? We don't know. But perhaps that's part of the beauty. The spiral reminds us that even in a world governed by laws, gravity, thermodynamics, relativity, mystery still thrives. There are still corners unlit, still questions worth asking, still shapes that spin on in silence, waiting for us to understand. So we keep watching, keep simulating, keep listening to the faint music of the arms, because the more we look at the spiral, the more it looks back. So far, we've seen the spiral from the outside, those glowing arms sweeping across the void, star factories curling in elegant arcs, rotating disks wrapped in invisible halos of dark matter. But here's the twist: you live inside one, and that changes everything. Living inside a spiral galaxy is like living inside a forest. From the ground, you see trees, trunks, leaves, patches of sky between branches. But only when you rise above, when you see the canopy from above, do you understand the forest's full shape. We don't get that overhead view. From Earth, the Milky Way appears not as a spiral, but as a band, a silvery river of stars stretching across the sky. We're embedded in one of its arms, the Orion Cygnus arm, sometimes called the Orion Spur, a minor branch between two larger arms, Perseus and Sagittarius. We can't see the whole structure directly. Dust blocks our view. Light from nearby stars outshines the distant arms. It's like trying to map your neighbourhood from a fogged-up window. But slowly, through decades of careful observation, we've pieced together the shape. Astronomers use infrared surveys to peer through the dust. They measure distances to stars. They trace radio emissions from gas clouds and star-forming regions. They observe the positions and motions of pulsars, variable stars, and young clusters. And bit by bit, the spiral takes form. We now believe the Milky Way has 4 primary arms, plus smaller branches and spurs. There's a central bar, possibly tilted slightly in our view, and a bright bulge of stars surrounding the core. The disk itself is warped, not flat but twisted slightly, like a vinyl record left in the sun. Above and below this disk, a halo of stars and dark matter extends outward, filled with ancient globular clusters and stellar streams, the remnants of smaller galaxies consumed over time. And at the very centre, of course, sits Sagittarius A, the supermassive black hole around which all of it orbits. From our position, about 27,000 light-years from the galactic centre, we are in a relatively quiet zone, far enough from the busy, star-packed core to avoid its chaos, not so far out that the spiral arms fade. We sit in a sort of cosmic suburb, where star formation still occurs, but life, including ours, has a chance to evolve in peace. It's worth reflecting on what this means. The Sun is not at the centre, not special, just one of hundreds of billions of stars in a rotating system, and yet that very ordinariness may be the key to everything. Because in a spiral galaxy like the Milky Way, conditions are just right. There's enough gas to make new stars, enough metals to build planets, enough stability to allow orbits to last for billions of years, enough dynamism to keep things evolving. If we lived in an elliptical galaxy, the story might be different. Less gas, fewer new stars, fewer planets, less opportunity for life. But spirals, they're like nurseries, not just for stars, but for potential. And here we are, looking up at the spiral from within, decoding it one light year at a time, riding through its arm on a small, warm planet, orbiting a modest star, inside the swirl, inside the story, and still turning. Now let's take a deep breath and step back, farther than the Milky Way, farther than the local group. Let's zoom out, not just in space, but in scale, and look around, because the spiral isn't just a galactic phenomenon. It's everywhere, in a hurricane, in a sunflower, in a snail shell, in the twist of a whirlpool, in the curve of a fingerprint, in the flight path of falcons and hawks as they circle their prey, in the double helix of DNA, in the very structure of some nebulae, where dying stars cast off gas in elegant corkscrews, even in protoplanetary disks, the rings of gas and dust around young stars, spiral patterns can form as newborn planets stir the material. The spiral is nature's signature, and it emerges not from whimsy, but from laws. In many cases, the spiral is a natural outcome of rotation and conservation of angular momentum. When a system spins and our material falls inward, it tends to flatten and spiral. This happens with galaxies, it happens with weather systems, it happens with water circling a drain, but it's more than physics, it's geometry. Many natural spirals follow a specific form called the logarithmic spiral, a curve that grows outward but never changes shape. The angle between the tangent and the radial line remains constant. It's self-similar, scalable, balanced. In other words, the same kind of spiral can appear in a galaxy 100,000 light-years wide, and in a seashell you can hold in your hand. Why? Because the spiral is efficient. It distributes force. It allows growth. It stores motion. It fits. Some mathematicians and physicists believe the spiral is a kind of universal attractor, a shape that systems naturally fall into when certain conditions are met. It's not imposed, it emerges. And that makes it all the more astonishing that when we look out into the universe, across billions of light years, the same pattern stares back. Galaxies twist into spirals, nebulae bloom in spirals. Even light from distant quasars, bent by gravity, can form spiral arcs through gravitational lensing. It's as though the spiral is not just a shape but a theme, a quiet refrain in the music of creation. Not because nature repeats itself, but because certain rhythms, certain movements, arise again and again when motion and time meet resistance and space. The spiral is what happens when the universe turns inward and forward at the same time. So the next time you look at a galaxy, or a rose, or a hurricane, or the back of a pine cone, know that you're seeing not just beauty, but continuity. Patterns that stretch from atoms to galaxies, from the breath of a storm to the arms of the Milky Way. Spirals everywhere. We often think of galaxies as places, and they are. They contain stars, gas, dust, and in at least one case us. But more than that, galaxies are machines of time, especially spirals, because a spiral arm is not just a shape, it's a clock. Not in the mechanical sense. There are no ticking gears, no numerals etched in star clusters, but spirals keep time through motion, through cycles, through changes so vast they stretch across epochs. Let's start with orbital time. As we know, the Sun takes about 230 million years to complete one orbit around the galactic centre. That means the last time we were in this same spot, in the Milky Way's orbit, give or take, dinosaurs were just beginning to rise. The continents were in different places. The world was unrecognisable. And the spiral arms, they mark density waves, regions of enhanced gravity and star formation that rotate more slowly than the stars themselves. So as stars orbit, they pass through the arms, like runners on a circular track, weaving in and out of traffic. Each time the Sun crosses a spiral arm, it enters a denser, more active zone of the galaxy. There's more gas, more stars, more ultraviolet radiation. Some scientists have speculated that these crossings could correlate with extinction events or climate shifts on Earth, not because of direct collisions, but because of subtle environmental changes. In that sense, the spiral arm is like a cosmic calendar, marking periods of activity and calm, creation and quiet. But the arms do more than just track stellar orbits. They also serve as a record of galactic history. Their structure tells us about past mergers, interactions, and internal dynamics. A warped arm might point to a passing satellite. A kinked bar might reveal a gravitational disturbance. By studying the shape of a spiral, astronomers can reconstruct the biography of a galaxy. In that way, the spiral is a memory. It holds the echoes of ancient events, encounters, waves, disruptions, preserved not in writing, but in motion. And spirals don't just mark the past, they shape the future. Stars born in spiral arms live out their lives, orbit the galaxy, die and return, enriched material to the interstellar medium. That material forms new stars, new planets, possibly new life. Each turn of the spiral brings more change, more possibilities, and this process, this turning, this cycling, will continue long after we're gone, long after Earth is swallowed by the Sun, long after the arms fade, long after even the spiral itself has dissolved into a quieter shape. Galaxies don't age like stars, they evolve. And for spiral galaxies, that evolution is measured in rotations. So while we may look at the spiral as a frozen shape, a still image in a telescope, it's better to see it as time in motion. A clock without hands, a calendar without dates, but always ticking, always turning, always moving forward. We've explored the science, we've traced the forces, followed the stars, mapped the curves of galactic arms. We've talked about gas and gravity, orbits and waves, dark matter and motion. But beneath it all, beyond the equations and models, the spiral still holds something deeper, a kind of quiet meaning. Because humans don't just observe, we interpret, we search, we wonder. And when we look up at a spiral galaxy, floating alone in the dark, it's hard not to feel something stir. Why this shape? Why here? Why now? We've long assigned symbolism to the spiral. In ancient art, it represented growth, life cycles, the movement from the inner world to the outer, or from chaos to order. Spirals appear in cave paintings, on pottery, in sacred geometry, always turning, always connecting. Even in modern times, the spiral shows up in unexpected places, in the way galaxies form, yes, but also in the path water takes as it drains, in the curl of a fern, in the swirl of galaxies, and in the shape of hurricanes that sweep our skies. Is that mere coincidence, or a reminder that all motion, from the microscopic to the galactic, is governed by the same deep rhythms? Some say the spiral represents infinity, a curve that never ends, always expanding. Others see it as a return, a loop, a cycle, a pattern that brings us back to where we began, but with greater understanding. Either way, the spiral draws us in. It whispers of something vast and yet deeply familiar, something out there and in here. Because even though spiral galaxies are impossibly far away, even though they shine with the light of billions of stars and stretch for hundreds of thousands of light years, we understand them. We build models, we run simulations, we give them names and catalogue their traits. But more than that, we stand beneath our own spiral, the Milky Way, and wonder. Wonder how we got here. Wonder why the universe chose this shape, this dance, this path. And perhaps, if you'll permit a moment of quiet reflection, the spiral is not just a cosmic structure. Maybe it's a question. Maybe it's the universe asking us to look deeper. Not just at the stars, but at ourselves. Because we too are made of cycles, of breath, of seasons, of thoughts spiraling inward and outward. We are, in a sense, galaxies of our own, billions of cells orbiting a single, fragile consciousness. Thoughts born, shaped, fading, returning. So when we look at a spiral galaxy, maybe what we're really seeing is a mirror of motion, of memory, of meaning. And in that mirror, we find both science and wonder. Every spiral has an edge, not a sharp one. Galaxies don't end like walls. There's no fence, no signpost saying, here the galaxy stops. But the spiral arms do fade. The stars thin out. The light grows faint, and eventually you reach a place where the darkness outweighs the glow. This is the galactic frontier, the place where the spiral dissolves into halo, and the disk gives way to open space. And it is not empty. Here in the cold and quiet outskirts of spiral galaxies, strange things happen. You find star streams, long, thin trails of stars, the shredded remains of smaller galaxies that ventured too close and were pulled apart by gravity. These streams twist like ribbons through the outer halo, tracing orbits shaped by a past long forgotten. You find globular clusters, dense balls of ancient stars, relics from the early days of galaxy formation. They orbit far beyond the spiral arms, like distant satellites, quiet, persistent, mysterious. You find gas, not the warm, star-forming clouds of the inner disk, but cold, tenuous hydrogen, stretching far into space, sometimes arranged in ghostly spiral arms that are invisible to the naked eye, but detectable in radio waves. These structures suggest that the spiral shape extends much farther than the stars themselves. You even find dark matter, or at least you sense its pull. The way stars move in the outskirts makes no sense unless there's something unseen guiding them. And that guidance, that extra gravity, is the shadowy fingerprint of the galaxy's massive dark halo. In this sense, the edge of the spiral isn't a boundary, it's a transition. From the luminous to the hidden, from the known to the inferred. And it challenges our idea of what a galaxy is, because most of a spiral galaxy's mass lies beyond the light, in the halo, in the dark, in the space where stars no longer shine, but gravity still holds sway. Think about that. Everything we see, the arms, the stars, the bar, the dust, all of it is just the central ripple in a much wider sea, a ripple that gleams for a time, that spins, forms stars, dances with companions, and fades. And in the outermost reaches, where light no longer guides us, we rely on subtlety, on motion, on distortions, on faint whispers in radio waves. It is in these outer zones that galaxies remember. They remember every encounter, every tug, every merger. Their outskirts are shaped by history, moulded over billions of years. And perhaps the most humbling truth is this: our solar system is not in the heart of the Milky Way, not in its bright centre, not in its densest arms. We live near the edge. Out here in the suburbs of the galaxy, we orbit quietly. We observe, we reflect, and maybe, just maybe, that quiet distance gave life a chance to flourish. The center burns too brightly. The arms can be chaotic. But at the edge, there's time, space, stability. So while it may seem lonely, the edge of the spiral may be the most fortunate place of all. A place to think, a place to wonder, a place to look back at the spiral and forward into the dark. We've reached the end of the spiral, or at least this spiral. 30 gentle turns through the arms of galaxies, one after another, unfolding quietly. One night, under the weight of 1 billion stars. And what have we found? We've learned that spirals aren't just shapes, they're stories. They begin in motion. A spin, a cloud, a ripple in gravity. Over time, stars ignite, arms form, patterns emerge, bars stretch across the center, gas flows inward, stars orbit outward. The spiral spins and changes and lives. We've learned that spiral galaxies are not static portraits, but processes, living systems that breathe, collide, grow, and evolve. We've seen how density waves carve paths through the disk, how dark matter holds the arms together, how satellite galaxies sculpt the spiral from the outside. We've watched stars form, die, and scatter their elements into the next generation, a chemical spiral written in the language of time. We've followed motion of stars, of gas, of galaxies themselves. We've listened to the spiral as a clock, a mirror, a pattern that appears across scales, from hurricanes to galaxies, from pine cones to DNA. We've stood within the Milky Way and looked both inward and outward. We've even touched meaning, that quiet space where science meets awe. And yet for all this, the spiral doesn't end here, because the universe is still spinning. Spiral galaxies are still forming. Stars are still being born in their arms. Supernovae still light the night. New patterns still emerge, traced in infrared and ultraviolet, drawn in hydrogen and helium. And we, brief sparks inside one of those arms, continue to look up, to ask, to model, to dream, because the spiral calls to something in us, something that yearns for understanding, yes, but also something that simply loves the curve, the symmetry, the quiet motion. It reminds us that the universe is not just big, it is beautiful. And that beauty is not just a byproduct of physics, it's part of the pattern. So the next time you look at a photo of a spiral galaxy, perhaps M51 or NGC 1300, or the ghostly swirls of our own Milky Way, don't just see stars. See time, see gravity, see memory, see yourself, because you are part of this spiral, your atoms, your thoughts, your place in the night. You are not separate from the galaxy. You are one of its quietest, most thoughtful arms, still turning, still wondering, still dreaming with the curious mind.